All right, are x equals 3 and x equals negative 2 solutions to the equation that explain how you know? Well, yeah, they are. If I have x equals 3, then this is 2 over 3, and this is 3 minus 1, so 2 over 3. 2 over 3 definitely equals 2 over 3. If I have x is negative 2, I've got 2 over negative 2. Negative 2 minus 1 is negative 3 over 3. 2 over negative 2 is negative 1. Negative 3 over 3 is negative 1. Negative 1 definitely equals negative 1. All right, solve each equation algebraically. Then verify your solution using graphing technology. Part A. So you got x plus 3 over x minus 1 equals 0. All right, so how do you make something equal 0? Well, the top has to equal 0. So x is negative 3. Part B. X plus 3 over x minus 1 equals 2. All right, so I would rather see this equals 0. Equals 2 is kind of harder. So what I'm going to do is I'm going to bring this 2 over. All right, one way to do it, we take the 2 and you subtract 2 from both sides. Now we have a 0 here. Now we're going to need a common denominator. Now there are other ways to do it, but I highly suggest you just do it using addition and subtraction to bring everything to the left and then deal with it from there. That way we won't have any issues when we get to inequalities. With inequalities, you have to worry about multiplying and dividing by negative or positive numbers. If we just bring everything to the left through addition and subtraction, then we could keep our methods the same no matter what kind of equations or inequalities we have. So bring the 2 over, you got minus 2. Now let's put the stuff together. All right, you get a common denominator by multiplying top and bottom by x minus 1. All right, to add or subtract rationals, we add the tops, or in this case subtract, and you keep the bottom of x minus 1. That's why we get a common denominator. All right, here we have an x minus 2x, that's negative x, and we have a 3 minus negative 2, so it's 3 plus 2, which gives us a 5. All right, I don't like to have negative x's. I like them to all be x plus something or x minus something, so I pulled out a negative 1 from the top. So you got negative 1 times x minus 5. So you see your leading coefficient is negative 1 here. And we have ourselves a rational with the same degree on top and on the bottom. That tells us something about the end behavior. It's going to approach an asymptote of negative 1. All that, of course, is assuming that we would write f of x equals negative 1 x minus 5 over x minus 1 and graph that, right? And I could talk on and on about what this graph would look like, but really we just want to know, when does it equal 0? Well, that's when this guy here equals 0, which is when x is equal to 5. Now don't make the mistake of saying x equals 1 is a solution, because when x is 1, then it's going to be something divided by 0. Well, something divided by 0 definitely doesn't equal 0. It equals, well, it's undefined, honestly. So x is 5 is our only solution here. It's only when the numerator equals 0 that we have a solution. Something I often forget to do in the homework is check the work, and I think it's important for you guys to check your answers. So how would we check this? X equals 5 is our solution, so let's go all the way back into the original and see if that's truly a solution to this. And when I say solution, I mean find an x value, or all the x values that make this true. So let's assume x really is 5. Then you got 5 plus 3 on the top, which is 8. You got 5 minus 1 on the bottom, which is 4. Well, does 8 divided by 4 equal 2? Yes, it does. So this is truly a solution. All right, let's look at part C here. So now we've got basically the same thing, x plus 3 over x minus 1, but now it equals 2x plus 1. So same thing, we want to bring everything to the left. So x plus 3 over x minus 1 minus 2x plus 1. Which I could also have said minus 2x minus 1. But let's get a common denominator. So we're going to say, we're going to multiply both. So this 2x plus 1 here. We're going to multiply top and bottom by x minus 1. And now I'm going to expand this. So 2x times x is 2x squared. 2x times negative 1 is minus 2x. 1 times x is plus 1x. So you got minus x. And 1 times negative 1 is negative 1. So there you go. That's just, I basically did FOIL. I FOILed these two things. And now we have a common denominator, so you can put them both over x minus 1. All right, so we've got x plus 3, and then we got minus 2x squared. So there's my minus 2x squared. You got your x minus negative x, which is plus x. X plus x is 2x. 3 minus negative 1, which is plus 1. So 3 plus 1 is 4. So negative 2x squared plus 2x plus 4 all over x minus 1. Again, this equals 0. Now remember, when it equals 0, all we care about is the top being 0, but the bottom can't be 0. If the bottom's 0, then it's undefined. So let's keep going. Of course, every time I try to factor, I try to take out a common factor first. So this negative 2 comes out, x squared minus x minus 2. And then this is a quadratic. It's x plus 1, x minus 2. The two numbers that multiply to give negative 2 and add to give negative 1, or 1 and negative 2. And we have it completely factored on top. And it has to equal 0. That means the top has to equal 0, not the bottom. Otherwise, it would be undefined. So the top being 0, x has to be negative 1 or positive 2. Negative 1 or positive 2. But double check. Make sure that negative 1 and positive 2 don't make the bottom equal 0. So negative 1 minus 1 is negative 2. We're good. 2 minus 1 is positive 1. We're good to go. Right, so these are our solutions. Of course, let's go double check in the original question. So let's start with x is negative 1. Negative 1 plus 3 is 2. Negative 1 minus 1 is negative 2. 2 over negative 2 is negative 1. And here, negative 1 times 2, negative 2 plus 1, negative 1. And negative 1 equals negative 1. That's good. Let's try it with 2. 2 plus 3 is 5. 2 minus 1 is 1. 5 over 1 is 5. And 2 times 2 is 4, plus 1 is 5. 5 equals 5. So those two are solutions. We are good to go. All right, let's do part D. So we have 3 over 3x plus 2 equals 6 over 5x. Now, like I said before, there are plenty of ways of doing this. You can multiply both sides by, I guess you can cross multiply, what you guys call it. But I'm just trying to stay consistent here, because when we solve inequalities, this is going to be the way that's going to be our best friend. So let's just stay consistent for now, and let's bring everything over to the left using subtraction and addition. So here we're going to subtract 6 over 5x from both sides, and that'll give us a 0. So we still have our 3 over 3x plus 2 minus 6 over 5x equals 0. So we just brought it to the left. Now we need to put these together, which means we need a common denominator. So we're going to multiply this side by 5x over 5x, and we're going to multiply this side by 3x plus 2 over 3x plus 2. Right? So you see the 5x over 5x and the 3x plus 2 over 3x plus 2. And that way, this has a common denominator, 5x, 3x plus 2, and 5x, 3x plus 2. Now we can put these guys together. So you got your 3 times 5x minus 6 times 3x plus 2. The bottom stays the same. Okay, this is 15x minus 18x minus 12. And just to be thorough on the bottom, I like to factor so that all of your factors are like x plus something, x minus something, and then we're just going to have whatever the leading coefficient is out front. So I needed to pull out this 3 so that you got 3x plus 2/3. And I'm going to pull out this 5, and the 3 and the 5 are going to multiply together to get 15 x plus 2/3 and x on the bottom. I'm just doing that to make sure that when I get a final answer, it doesn't also make the bottom equal to 0, because if it does, then my final answer isn't an actual answer, because you're not allowed to have the bottom equal 0. So I just make sure that everything's factored nicely. So you see the bottom, it's got, now I know that x can't be 0 and x can't be negative 2/3, because that would make the bottom 0, which is not allowed. Right, so if my answer was x equals 0 or x equals negative 2/3, I'd say, uh-oh, that doesn't count. Or I could even go plug it in, and I would see that negative 2/3 can't be there, and 0 can't be there, because it would make the bottom 0. Anyway, that's a lot of stuff to say, just to say that I love to factor both top and bottom. All right, so 15x minus 18x is negative 3x for the top, minus 12. Again, I like to factor, so it's always x plus something, x minus something. So I'm taking out this negative 3, and we get negative 3, x plus 4. Now, how do you make something equal to 0? You make the numerator equal to 0. Now that it's all factored, just make the numerator equal to 0. And that means the whole thing will equal 0. So how do you make the numerator equal 0? X equals -4. There it is. And just to double check, -4 doesn't make the bottom 0, which is good news. We don't want 0 over 0. We just want 0 over something else. And so the answer is -4. Let's check our answer. Put a -4 here. We got 3 times -4 is -12. Plus 2 is -10. So 3 over -10. And here we're going to get 6 over -20. And sure enough, 3 over -10 is the same as 6 over -20. All right, this wasn't part of your homework. Number 3 wasn't included, but again, this is just such a nice question to do, and it's going to be so easy to do, so I'm just going to do it for you. So 3 says, for each rational equation, write a function whose zeros are the solutions. So function means it needs to pass the vertical line test, which means you need an x and a y variable. So I'm going to introduce a y variable, and its zeros have to be the solutions to this. All right, so whenever my function equals 0, that's going to be the solution to this. Well, the key to that is, first of all, let's rewrite the first equation with everything to the left. So x minus 3 over x plus 3 minus 2 equals 0. And so the solution to this is whenever all of this equals 0. So if I want to write a function with a 0 that has the same solution, I just say f of x equals x minus 3 over x plus 3 minus 2. Right? So when this equals 0, that's a solution to this problem. When 0 equals 0, that's a solution. But also, when this equals 0, that's when f of x equals 0. So on my graph, that's when it would hit 0. So what I just did is I took this rational equation, I wrote a function whose zeros are the same as the solutions to the equation. It's pretty easy, right? You just bring everything to the left and then just say f of x equals that. So let's do b. So again here, so there's there's an equation here. Bring everything to the left, so 3x minus 1 over x minus 5/2 equals 0. And now the answer for x that makes this 0 is also the zeros for this function, because it'll make this 0 as well. Done. Let's do c. And I'm going to even skip this step. I'll just go straight to the answer for c. All right, there it is. H of x is x minus 1 over x minus x plus 1 over x plus 3. Right, because I just bring that over, it'll equal 0. And of course, that's what this, when that equals 0, that's the 0 for h of x. This one is graphable. If I graphed this, I would have an h of x, like a vertical axis, and an x horizontal axis. And whenever this equals 0, it would equal 0 on my x-axis. This one is not graphable on with two axes because there's only one variable. But the solution to this is whenever, if I bring this to the left, it'll equal 0. So whenever that side, this thing here, equals 0, that would be a solution. So you see how the solutions of an equation correspond to the function if you bring everything to the left and make it equal to 0. So to the zeros of the function. So you can always just bring everything to the left, make it equal to 0, let f of x or g of x or h of x or I of x equal that thing, and its zeros are the solution of your original. So if I find the zeros here, then I could go back up and say, therefore, x equals those solutions for here. And for part D, you can see it's simple. I just say I of x equals x minus 2 over x plus 3 minus x minus 4, x plus 5. Just bring everything to the left, and then just let your function equal that. And then the zeros of this is your solution to this. And there it is. I should have known. Number 4, solve each equation in question 3 algebraically and verify your solution using a graphing calculator. So I thought I was being all nice by doing question 3, but I would have had to do it anyways to solve for question 4. So let's go with A. We have to solve this guy. Now keep in mind, all we really need to do is find out when this equals 0. So once I get a common denominator, put all this together, and then factor the top, I'll know my answer. It's just when the top is equal to 0. But I'm going to go a step beyond that. Now that I have f of x equals this, I'm going to actually just graph the whole thing, and then we'll look at the graph. It'll be basically the same thing, but I want you to see graphically how you know when this equals 0. So we're going to get a common denominator here. So this minus 2 is going to be minus 2 x plus 3 over x plus 3. That way they're both over x plus 3. Now we can put the tops together and keep the bottom. All right, so to put them together, you got your x minus 3 minus 2x minus positive 6. Keep in mind, this is minus all of this. So that since this is a 2x plus 6, we're subtracting all of that. So it's minus the 2x and minus the positive 6. All right, we're going to put that together. So x minus 2x is negative x. Negative 3 minus 6 is negative 9. All right, you guys know that I hate negative x's anywhere. I like it to be x plus something and x minus something. So I'm going to take a negative 1 out of the top here. I got negative x plus 9 over x plus 3. And I'm going to graph this. Now, by the way, we already know the answers, the solution. I know I'm making this hard on myself. I know the solution is just x equals negative 9. But I want to graph this so that you guys can kind of see how the graph relates to the solution. All right, now I need you guys to really be taking this seriously. Like, don't just listen to me talk and just let it all go over your head expecting to later understand. Like, I want you to rewind and check if there's anything you don't understand about this. So we have a degree 1 divided by a degree 1. They're both the same degree. And so the end behavior to the right is going to be a horizontal asymptote at negative 1 over positive 1. And that's negative 1 over positive 1 is negative 1. So I'm going to draw a horizontal asymptote at negative 1. Let's just move this over a bit. All right, since it's all factored form, this is actually going to be really easy. So when the bottom equals 0, but the top doesn't, so at negative 3, we're going to have ourselves a vertical asymptote. When the top equals 0, but not the bottom, we're going to have ourselves a 0. And by the way, this is the solution, because we're just looking for when f of x equals 0, right? This is your f of x equals 0. So when x is negative 9, we have a 0. All right, and last, we know that the end behavior is going to be near this negative 1. So let me just plug a big number in here. So let's say 1,000. 1,009 over 1,003. So it's actually negative 1,009 over 1,003. 1,009 is just a tiny bit bigger than 1,003. So that's going to be 1,009 divided by 1,003 is going to be a tiny bit more than 1. So it's going to be negative 1 point something. So that means we'll be just a little bit under this vertical asymptote. So negative 1 point a tiny bit. Another thing we can do is plug in x is 0. That'll find our y-intercept, or sorry, our f of x intercepts, or f of 0 here. F of 0 is 0 plus 9, so negative 9 divided by 3, which is negative 3. And I'm pretty sure we have all the information we need here. We know how these rationals behave. It's going to go through here. It's going to go down to our asymptote. Notice that x plus 3 here is only degree 1, so it's order 1, which means the other side of this asymptote is going to come from the other end. It needs to go through this 0 and go off along this horizontal asymptote. Now this looks all good. I just want to show you that see how it's a little bit above the horizontal asymptote here and a little bit below? Well, let's just check a negative big number. So let's say I have negative 1,000. Negative 1,000 plus 9 is like negative 991. And negative 1,000 plus 3 is like negative 997. And those two negatives will cancel each other out. But notice that now that the negative 997 is a little bit bigger. So the top is a little bit smaller than the bottom. So that means it's going to be a little bit less than 1. And it'll still be negative, so negative like 0.99. And so you'll see it'll be a little bit above the asymptote. So you see how that works, where when you plug in a positive number, because this is a plus 9 and that's a plus 3, the top will be bigger. When you plug in a negative number, because this is 9 and this is 3, it'll actually be a little bit smaller. And so you're going to often have one on one side and the other on the other side. But in case you're just not really good at doing that in your head, just plug in negative 1,000. See what happens. See if it's negative 1 point a little bit, meaning it's a little bit lower, or 0.99, which means it's higher. Do the same thing with positive 1,000. Just check to see if this line's a little bit less or a little bit more if you need to. And if there's anywhere on this graph that you're unsure, plug in a -9, make sure it equals 0. Plug in a 0, make sure it equals -3. Heck, plug in a 2 and see if it equals somewhere in between -3 and -1. Let's plug in a 2. 2 plus 9 is 11. 2 plus 3 is 5. So -11 divided by 5. Well, that's going to be -2.2. And that's about where this is, right? So you have a spot at 2, -2.2 here. Okay, I very much realize that the question didn't ask us to do any of this. All it asked us to do is solve the equation. And this equation is, when is this equal to 0? So we let f of x equal this. And so when this is equal to 0, my function will be equal to 0 because it's the same thing. So I just look, when is it equal to 0? The function is the height, right at -9. So your answer is -9. Okay, and yes, I do realize that as soon as I had this thing factored on the top, right here, I knew that -9 was my answer, right? But I did want to show you all of this because eventually we're going to get into rational inequalities where you're going to have to see when it's greater than 0 or less than 0. And if you can draw the graph every time, yeah, we can see when it equals 0, no problem. But now we could also see when it's greater than 0. Anything between -9 and -3, it's greater than 0. We can also see when it's less than 0. Anything below the x-axis is less than 0. This is where the negatives are. And so anything to the left of -9, so between -infinity and -9, and anything to the right of -3 all the way up to infinity, that's where it's below the x-axis. That's where this is negative. Between -9 and -3 is where this is positive. So if you plug in a -6, I guarantee you're going to get a positive number here. And right at -9, that's the one spot where this will equal 0. Okay, so graphing this is unnecessary when you're just trying to find out when it equals 0. All you have to do is make the top equal 0, as long as the bottom doesn't. But graphing it will become very, very, very useful when we get into inequalities, so you might as well get used to it now. Another thing you're going to hear me say all the time is get that top factored, get that bottom factored, because then you don't have to keep second guessing yourself. You know where all your zeros are, you know where all of your asymptotes are, you know the leading coefficients in case you need that as well for the end behavior. All right, let's try part B. All right, just for thoroughness and just so that you get the most out of this, I'm going to do this in two different ways. I'm going to do it the easy way and the more complicated way, but more useful way for our future. So I want you to both understand both of them. So for this one, I'm letting g of x equal our equation with everything to the left. And here I'm just saying, hey, when is it equal to 0? So this is what we're actually solving. And this is what I'm making the whole function equal to this. And then at the end, I'm going to look at our graph and just see when this equals 0. Definitely the harder thing because I'm graphing the whole darn thing. Here I'm just looking for the zeros, okay? So first things first, I have a rational minus a rational, so I'm going to get a common denominator. So I multiply top and bottom by 2 here, and I multiply top and bottom by x over here. Same thing over here, but this time it's g of x equals instead of 0 equals. All right, here the easy way, just take this is 6x minus 2 minus 5x, and it's all over 2x. Same thing over here. This one I'm saying is equal to g of x, so I could graph the whole thing. This one I'm only concerned about when it's equal to 0. All right, so the actual solution here is just when is the top equal to 0, but not the bottom. So the top is equal to 0 when x is 2. Just check the bottom, and we're okay. It won't equal 0 if x is 2. It'll be 0 over 4. And so our solution is x equals 2. Let's do a quick check up here. If x equals 2, then we're going to have 6, 2 times 3, so 6 minus 1 is 5 over 2, minus 5 over 2, yeah, that equals 0. Or better yet, let's go right up to the source. So 6 minus 1 is 5 over 2 equals 5 over 2. So yep, 5 over 2 definitely equals 5 over 2, so x equals 2 is a solution. Now on the other side here, g of x, this is completely factored. So I can actually really quickly graph this. This is degree 1 over degree 1, which means it's going to hit a horizontal asymptote at 1 divided by 2, so 1/2. So I'm going to make a horizontal asymptote at 1/2, right? It's going to have a vertical asymptote when the bottom equals 0, but not the top. Okay, so the bottom equals 0 when x is 0, but not the top. So at x is 0, we have ourselves a vertical asymptote. And it's going to have a 0 when the top is 0, but not the bottom. So 0 at x is 2. There we go. And now I can just start graphing. I know it hits this horizontal asymptote. I know it comes through 2. I know it must go down this asymptote. Now just to double check, x minus 2 is not, it's not x minus 2 squared, so it doesn't bounce off this and go back up. It goes right through it. This 2x, so it's 2 times x minus 0, that's not squared, so it's going to come down negative and it's going to come back up from the positive, or back down from the positive. And so it's going to come this way, and then it's just going to meet up with our asymptote over there. So a very simple graph. And now our question is asking, when is this equal to this? Which means when is this equal to 0? And this is what I graphed. I let g of x equal that, and I graphed it. And when is it equal to 0? Well, let's just check. Aha, when x is 2. So the answer is at x equals 2. And of course, we already knew that from over here. Same thing here. But I like it again, because if I were to ever ask you this question again, but I said, when is 3x minus 1 over x greater than 5/2? Well, then you would bring the 5/2 over to minus 5/2, and you want to know, when is it greater than 0? Okay, and that would all happen when this graph, we can say when this is greater than 0. So this is g of x. So this is greater than 0 when g of x is greater than 0. And that's all when x is negative infinity all the way to 0. And then on the other side of 0, it's now smaller than 0. Like the y value is smaller than 0 all the way to 2. And then again, it's greater than 0. So you could say that g of x is greater than 0 from negative infinity to 0, and then again from 2 to positive infinity, right? And if I ask you, when is this less than 5/2, then we could say, we can carry that over, and we could say, when is this less than 0? And then since we graphed it, we can just look to see when it's less than 0, and that's between 0 and 2. Okay, so you can see how this will be useful when we have inequalities, so you might as well get used to it now. I keep saying that. Now for C and D, I'm just going to solve, and I'm going to leave this for our actual inequalities when we get there. All right, part C. When does this guy equal this guy? Well, I'm going to bring this over to the left side and make the right side equal 0. So when is this equal to 0? Of course, we're going to put these two guys together by getting a common denominator. So you see I multiply this one by x plus 3 over x plus 3, and I multiply this one by x over x. Now they both have a common denominator of x plus 3 times x. Now I can put these two together. You got x squared plus 3x minus x, that's plus 2x minus 3. And this is x squared plus x, and you're subtracting those. So x squared minus x squared is nothing, that goes away. 2x minus x is just x, and negative 3, no, there's nothing to subtract, so just x minus 3 on the top, x plus 3 on the bottom, and x on the bottom. The things that make the bottom 0 are negative 3 and 0. We have to be careful of those, because you're not allowed to use those in your answers, because x is never allowed to be that. The only solution is when the top equals 0, because the only way to make something equal 0 is to make the top equal 0. So the only solution is x equals 3. And we're safe. When x is 3, we got 0 over 6 times 3, 18. This isn't 0 on the bottom, so we're good. So x equals 3 is our solution. And let's just plug it in to double check. So 3 minus 1 is 2, and 3, so 2/3. is equal to 3 plus 1, so 4 over 6. 2/3 indeed is equal to 4/6. They're both equal to 0.6 repeated. So there you have it. Now I could have graphed. It would have taken a really long time. And my only zero, if I let's say, h of x equal this, the only time it would cross that x-axis is when x is equal to 3. And we would have asymptotes at -3 and 0. And then I could tell you the end behavior would be a horizontal asymptote going to 0 because the degree on the top is smaller than the degree on the bottom. And we know a whole bunch of stuff to graph it. But the answer is x equals 3 because all we care about is when it equals 0. So where the zeros would have been. All right, last one, part D. When is this equal to this? Well, I bring this over to the left right here and make it equal to 0. So we just have to find out when this equals 0. Hopefully you figured out my method of doing it. You get a common denominator. So this one's going to be times x plus 5 divided by x plus 5. This one's going to be times x plus 3 divided by x plus 3. Now they have the same denominator. Let's put the numerator together. Now, little by little, I'm going to do less steps so that you guys can figure out quicker ways of doing this. But as you can see, this is going to be x squared plus 3x minus 10. You guys know how to FOIL. This is going to be x squared minus x minus 12. But since we're subtracting, it's minus x squared plus x plus 12 because minus x is plus x, and minus 12 is going to be a plus 12. Remember, we're subtracting this whole thing. So you have to subtract each term that you get out of there. All right, so this x squared gets rid of that one. They cancel each other out. You got 3x and 1x, that's 4x. Negative 10 plus 12, you got 2. You can take out a 4 from here. All right, we have 4 times x plus 2/4 or 1/2, same thing. And we can clearly see this is nice and factored on the top and on the bottom. And when is it going to be 0? Well, not when the bottom's equal to 0, only when the top is 0. If the bottom's equal to 0, that's undefined. And undefined does not equal 0, so that's not a solution. So when x is -1/2, that's your solution. Just double check, make sure that that doesn't put a 0 on the bottom, and it doesn't. So yes, x is -1/2 is your solution. And if you want to check it in here, be my guest. It'll work. All right, number 5, solve each equation algebraically. All right, well, I know to bring this 7 over x to the left. Now, I'll keep reminding you guys, there are definitely other ways to solve this. I guarantee it, but I'm just going to stay consistent. I'm just going to keep bringing things over to the left by subtracting them. And it's one way that you can just consistently solve rationals, all right? So we have 2 over that x plus 5 over 3 minus 7 over x. A common denominator would be 3x. So there you go. You multiply this one by 3, this one by x, and this one by 3. Now put the top together. You got 6 minus 21 is -15, and you got 5x minus 15 over 3x. You know I'm always going to factor so that we get x plus something, x minus something in all our brackets. Take out the leading coefficient, and here we go. To make the top 0, x equals 3. That's our answer. Just double check, make sure that the bottom doesn't also equal 0. So when x is 3, this will be 9. We're all good. So x equals 3 is our final answer. Part B, I'm going to start skipping steps a little bit. I'm going to bring the 6 to the other side, but at the same time, I'm going to make sure they all have a denominator of x plus 3 times 3, just to save some time. So multiply this one by 3 over 3. I multiply this one by x plus 3 over x plus 3. And I multiply this one by 3 times x plus 3 over 3 times x plus 3. This one needs a 3 and an x plus 3 to have a common denominator. So this 6 times 3 is 18, and x plus 3 over x plus 3. So there we go. Now we can put the numerator together and keep the bottom. Here you got 10 times 3 is 30, 10x plus 30 minus 18x minus 54 all over 3x plus 3. Put the 10x and negative 18x together. You got minus 8x. Put the 30 minus 54. You got plus 6. Take out a negative 8 so that it's just x plus something or x minus something here. So it's actually negative 8 times x minus 6/8, but 6/8 can be reduced to 3/4. And we know what our 0 is. It's when x equals 3/4. And just check on the bottom, make sure that 3/4 doesn't make this 0, which it doesn't. So x equals 3/4 is our final answer. All right, I think I could do one more for you, and then I'm sure you can handle D, E, and F just by doing it the same way. So here we have 2 over x minus 3. We're going to bring the 1 over, so it's going to be minus 1, but we're going to get a common denominator of x minus 3 over x minus 3. We're going to bring the minus 6 over x minus 3 over by adding it, so plus 6 over x minus 3, and on the right we're left with a 0. The bottoms are all the same because I got the common denominator. Let's put the top together. All right, here you have 2x minus x, that's just 1x. You've got minus negative 3, so that's positive 3. And you got plus 6, so positive 3 plus 6 is plus 9. So x plus 9 over x minus 3. And when does that equal 0? When x is negative 9. Just make sure that at the bottom, negative 9 minus 3, that's negative 12. That doesn't equal 0. Okay, we're safe. It doesn't equal 0. So the answer is x is negative 9. All right, I really don't feel like there's anything new here. Maybe I'll choose one of them. Let's do part C. There's a squared in there. Maybe it'll be a little bit different for you. So I'll do that one. You guys could do the rest. All right, so we have 2x over 5. I notice there's a 5x over here, though, so I just took the liberty of multiplying top and bottom by x to get a common denominator. I brought this over to the left, so you got minus x squared minus 5x over 5x. You already have your common denominator. 8 equals 0. Let's put the top together and keep the bottom. We can see 2x squared minus 1x squared is just x squared, and minus negative 5x is plus 5x. So x squared plus 5x over 5x, and let's take out a common factor of x. Ooh, it looks like they're trying to be tricky here. They've got an x on the bottom and an x on the top. Let's cancel those guys out like that, and we can't do that without writing comma. X cannot be 0. And now let's see what happens. How does our top ever equal 0? Only when x is negative 5. So they might try to trick you into saying when x is 0, you have a solution. But when x is 0, that's not a solution. Look at when x is 0, this side is undefined. And undefined does not equal 0. So it doesn't work. So that's why I like to bring everything to the left, factor it. And you guys are going to see that factoring is really where it's at in this class. The better you can factor, the easier your answers are going to be afterwards. And so your final answer is only x is negative 5. Okay, like I said, I'm going to let you guys do the rest. I'm just kind of checking these ones over. I think the common denominator here is going to be x minus 1, x plus 1. The common denominator here is going to be x plus 2, x plus 3. So be careful. This 13, when it comes over, is going to be minus 13 times x plus 2 times x plus 3, which will be, you're going to get an x squared plus 5x plus 6. There's a lot to do there. The common denominator here will be x minus 2. Everything's already on the left. That's convenient. The common denominator here will be x times x plus 1. So you're going to have to do both of those to this. X times x plus 1 is just x squared plus x. And so, yeah, there's a lot to do here. If you have any trouble, let me know. But I think you guys should be capable by this time. All right, again, I don't even encourage you guys to do all 6 of these. It's all the same thing. Let me just choose, let's say, E. All we're going to do is bring everything to the left again, and then I'm going to graph it and see when it equals 0. Now, to graph it, you need an x and a y. So I'm going to have to let f of x equal 2x plus 3 over 3x minus 1 minus x plus 2 over 4. Now that I do that, I can graph it. Here it is, and the answers are wherever f of x, which is this, equals 0. That's what we're looking for, is when this f of x is equal to 0. So this is not equal to 0 here. I know the x value is equal to 0, but we want to know when f of x is equal to 0. This whole thing is equal to 0. When x is 0, the answer is negative 3.5. Well, negative 3.5 is less than 0. So don't confuse this as one of the zeros. The zeros are negative 1.717 approximately and 2.717 approximately. And that's when those are the x values that make this function equal to 0. If this were greater, what am I doing? See here? No, E. So if this were greater than 0, then when I brought this over, or sorry, greater than x plus 2 over 4, then when I bring this over, it would be when is it greater than 0, and my answers would be anything less than negative 1.717, and anything between 0 and 2.717. If this said less than this side, then it would be anything that's less than 0 would be our solutions. So this graph it would be anything between negative 717 and, oh, it's not even 0. It's wherever this asymptote is, which is at like 1/3. My bad. It's at 1/3. And anywhere from, so negative 1.717 to 1/3, and anywhere from 2.717 to infinity. That being said, if this is an equality, like it's an equation, my bad, and so this is when it's equal to 0, so here are the two solutions. Round your answers to two decimal places, so I should have said negative 1.72 and 2.72 are my solutions. So this is actually a much easier question than before. It's saying solve using graphing technology. All you have to do is just bring everything to the left and then put that into Desmos, let it graph, and since you brought everything to the left, then the right side will just be 0. So when you let f of x equal that thing on the left, that you just have to find out when f of x equals 0, and that's just going to be all the spots that are crossing the x-axis. So that gets quite easy if you're allowed to just graph it. All right, I really don't feel like there's much different here, but I'll do one more of these. So solve this, explain my steps. Step 1, bring everything to the left side using subtraction from both sides. So you're going to subtract x plus 3 over x minus 4 from both sides. On the right, you're just going to get 0. It's gone. And on the left, you're going to get that. Step 2, get a common denominator. So x plus 1 over x minus 2 has to be multiplied by x minus 4 over x minus 4. This guy has to be multiplied by x minus 2 over x minus 2. That way this one has an x minus 4 and an x minus 2, and so does this guy. And we can put the numerator together, or just add them up with the common denominator here. All right, so you should expand this. So this is going to be x squared minus 3x minus 4. And this is going to be minus x squared. And then it's going to be plus 3x minus 2. It says plus x. So it's minus plus x, which is minus x. And this is going to be negative 6. So minus negative 6, which is plus 6. And so you expanded both of these and simplify the numerator here. Step 4, we're going to factor the numerator, and if necessary, this includes factoring out the leading coefficient. And step 5, your answer is anything that makes the top equal 0, but not the bottom equal to 0. Part B, I'll just do this orally. Verify your answer in part A using substitution. You just have to look here. Let's let x be 1/2. So this is going to be 1.5 on top, and 1 minus 2, 1/2 minus 2 is negative 1.5. Well, 1.5 divided by negative 1.5 is just negative 1. Let's look here. If x is 1/2, you got 3.5 and negative 3.5. Well, 3.5 over negative 3.5 is also negative 1. So negative 1 does equal negative 1. This is indeed a solution. All right, part C is pretty easy, so I might as well do it. Verify your answer in part A using a graphing calculator. So here's the graph. All I did is take everything, put it to the left. So you have x plus 1 over x minus 2 minus x plus 3 over x minus 4. I don't have to put all this stuff together if I don't want to, because the graphing calculator can handle this. When is it equal to 0? We can just kind of look over here. Y is equal to 0 when x is 0.5 right here. And that's the only place it hits the x-axis, so that's the only solution. And of course, that's what we got, x equals 1/2. And just let's look at this graph a little closer, just to kind of go over all the stuff we know. This is the simplified version that's all factored. Sure enough, the only 0 on top is x equals 1/2, and that's why we got our only 0. We have an asymptote at x equals 2 and another one at x equals 4. So here's x equals 2, x equals 4. You see you have your asymptotes. They're both order 1, so they're going to come in from one side and come out from the other, down, and it comes from up here. You can see that the degree on the top is degree 1 and the degree on the bottom is degree 2. So since it's a larger degree on the top, this whole thing will approach 0 when you go off to positive and negative infinity. And you can see that's what happens over here and over here. Let's even look at a big number. So let's say 100. This is going to be positive, 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 negative. So even though it's going towards 0, it will be negative. And sure enough, it is underneath the x-axis. So it is negative. So all the things that we know, we come here, there's no zeros, so it's got to stay negative. Approaches your asymptote. Since it's only an asymptote like the order 1, this x minus 4 here, that means it's not going to come back from the same direction. It's going to flip to this side. It's going to come down and back up, and this is also order 1, so it's going to flip back to here. It's going to go through at 0.5 because that's only order 1, so it's not going to bounce off. It's going to come up, and then of course because it has to approach 0 and the end behaviors, it comes back down and approaches 0 from the top because there's nowhere else to get through this x-axis. All right, number 9. Good. We get to actually do some word problems. So the Greek mathematician Pythagoras is credited with the discovery of the golden rectangle. This is considered to be the rectangle with the dimensions that are most visually appealing. This golden rectangle happens in nature all the time as well, but it's also things that famous painters will use that type of rectangle to do their paintings because they say it's the most appealing to us. In a golden rectangle, the length and width are related by this proportion. A billboard with a length of 15 meters is going to be built. All right, so we're going to replace the length with 15 meters there and there. What must its width be to form a golden rectangle? All right, we just have to solve for W. All right, you guys have learned me now. First thing I do is move everything to the left. So we got the W over L minus W on the left. So subtract that from both sides. Replace the L with 15 because that's what it says it is. And now let's solve for W. We're going to need a common denominator here. So this one has to be multiplied by 15 minus W on the top and bottom. This one should be multiplied by W, both top and bottom. And you got 15 times 15 minus W minus W squared all over W times 15 minus W equal to 0. Simplified, we got 225 minus 15W minus W squared. Let's rearrange it so the highest degree is on the left and the lowest degree is on the right. Take out the negative 1. That way we have our leading coefficient there. All right, to solve this, we just have to find something where the numerator equals 0, but not the denominator. This doesn't look like it's going to be easy to factor necessarily, so since it's a quadratic, I can just use the quadratic equation because we're going to want to see when W squared plus 15W minus 225 equals 0. And so W will just be, we all remember the quadratic equation. You got negative B, so negative 15, plus or minus. So I'll do the plus over here and the minus over here to get both answers. The square root of B squared minus 4AC all over 2A. So on this side we get approximately 9.27, and over here we get approximately negative 24.27. Now, I don't think that you can have a width of negative 24.27. That doesn't make any sense. So we're going to call this one inadmissible. Don't call it undefined. It's defined. It's just not in our range. It doesn't make any sense for this question. So we're not going to admit that into our answers. It's inadmissible. So this one is our actual answer. Its width must be about 9.27 meters. And I always like you guys to verify that 9.27 doesn't make the bottom equal 0. Well, the only things that make the bottom 0 are 15 or 0. So as long as we didn't get 15 or 0, we were okay. So this is a correct answer. Number 10, the Turtle Dove Chocolate Factory has 2 chocolate machines. Machine A takes S minutes to fill a case with chocolates, and machine B takes S plus 10 minutes to fill a case. Working together, the 2 machines take 15 minutes to fill a case. Approximately how long does each machine take to fill a case? All right, because we got variables here, and I know high school students are better off like kind of finding a pattern before they do anything, so let's just say S minutes. Let's just say that that's 5 minutes. So let's say it takes 5 minutes to fill one case. All right, so how many cases do they fill every minute? Well, if it takes them 5 minutes to fill only one case, well then in 1 minute they're not filling a full case, they're only filling 1/5 of a case. All right, let's say it takes 50 minutes to fill one case. Well then in 1 minute, again, I'm only filling 1/50th of a case. I'm pretty sure that pattern goes for everything. If it takes S minutes to fill one case, well then I'm going to fill in 1 minute, I'm going to fill 1 over S cases, or 1 over S case. So this is our general term. So if it takes me like 4 minutes to do one case, then in 1 minute, which is a quarter of the time, well, I'm only going to do a quarter of those cases. If it takes me 100 minutes for one case, that means each minute I only did 1/100th of the case. So any number, S minutes, it's going to do one case, means it takes me in 1 minute, I only do 1 over S cases. That's the general term. And that's the exact situation with machine A. It takes S minutes to fill a case. And so in 1 minute, it'll fill 1 over S cases. Machine B takes S plus 10 minutes to fill a case. So in S plus 10 minutes to fill one case. So in 1 minute, it fills 1 over S plus 10 cases. And working together, the two machines take 15 minutes to fill a case. So 15 minutes to fill a case, that means in 1 minute, they fill 1/15th of a case. So let's see, machine A in 1 minute fills 1 over S cases. 1 over S. That's the total amount that is filled after 1 minute from machine A. Machine B fills 1 over S plus 10 cases. So that's in 1 minute. So in 1 minute, that's how many cases are being filled, right? You got this guy fills, machine A fills that much, and machine B fills that much. And that's a total of, in each minute, you can add those together for the total, but it's also, it says, working together, the two machines take 15 minutes to fill a case, so that means each minute they fill 1/15th of a case. So these two numbers together is how much they fill, but also 1/15th is how much they fill. So these are equal. And since we know these are equal, that means we have an equation and we can solve it. And look, it's a rational. That's good news. We know how to solve rationals really, really well. Bring everything to the left. Get a common denominator. You have an S plus 10, and a 15. You need all three of those. All right, now let's expand the top and simplify it. Also take out the negative leading coefficient there, -1. And as usual, for this to equal 0, which would solve our problem, the top has to equal 0, but the bottom can't. So here, I don't know how easy it'll be to factor this, but since it's a quadratic, I could just use the quadratic equation. The quadratic equation is reserved for a quadratic that has to equal 0. So if it has to equal 0, we can say S equals -b, so 20, plus or minus the root of b squared minus 4ac, so 20, well, -20 squared minus 4 times 1 times -150, all over 2a, which is just 2 times 1. And using our calculator, we see that S can be 25.81 or -5.81. Well, -5.81 says that means that A takes -5.81 minutes to fill a case with chocolates. That does not make sense in our context, so we will say that is inadmissible. And that means S must be 25.81. Therefore, machine A takes about 25.81 minutes to fill a case, and machine B Takes about 35.81 minutes to fill a case. So that's about, what, 25 minutes and 48 seconds, and 35 minutes and 48 seconds, a little bit more. Taylor purchased a large box of comic books for $300. She gave 15 of the comic books to her brother and then sold the rest on an internet website for $3.30, making a profit of $1.50 on each one. How many comic books were in the box? What was the original price of each comic book? All right, so we have a box of, I don't know, N books. We'll say there are N books, and it costs $300. All right, so each book costs, I don't know, 300 over N. That's the price per book. Right, you divide it by the number of books. Okay. And then she sold it. Now we got another box, and this time there are less books. There are N minus 15 books, and that costs $330. And so each book there costs 330 divided by N minus 15. Right, so that's the new price per book. And we're told that the new price per book is $1.50 more. So this new price per book, so this guy plus $1.50 should equal the new price. Right, we're saying that the new price is $1.50 more, so the old price, the lower price, plus $1.50 should equal the newer price. So here we are. Now we need to solve for N here so that we can go back and say what was the original price, which is right here, 300 divided by N. All right, as soon as we find N, we'll know that the original price is 300 divided by N. All right, so let's clean this up a little bit. Get that equation in a nicer form there. So by now you know the routine. Subtract 330 over N minus 15 from both sides to get 0 on the right. Let's get a common denominator of N times N minus 15. Now we'll expand all these. Let's add all the numerators together. Collect like terms, put them in order, take out the leading coefficient. All right, this is even factorable. Two numbers that multiply to give negative 3,000 and add to give negative 35 are negative 75 and positive 40. And so here we are. It's nice and neat. We have it factored on top, factored on the bottom. So when does this equal 0? Well, it's when the top equals 0, but the bottom doesn't. So N must be 75 or negative 40. But what does N represent? N is the number of books in our original box. So I don't think N is allowed to be negative 40. There weren't negative 40 books in the original box. So that is inadmissible. So there must have been 75 books in the original box. Now the question says, what was the original price of each comic book? Well, the original price was 300 divided by N. So if N is 75, 300 divided by 75 is 4. So the original price was $4. Let's double check if that makes sense. So she purchased comic books for $300. There were 75 books, each $4. That cost $300. That makes sense. She gave 15 away, so now she only has 60 books. And then she sold them for $330. So if you have 60 books and you charge, it's $1.50 more, so you're charging $5.50, and that times 60, sure enough, equals 330. 60 times $5.50 equals 330. So this all makes sense. So the original price really was $4. The new price was $5.50. All right, polluted water flows into a pond. The concentration of pollutant C in the pond at time t minutes is modeled by this equation, where C is measured in kilograms per cubic meter. All right, when will the concentration of pollutant in the pond reach 6 kilograms per cubic meter? So C, we want to be 6. Okay, well, we'll just let C of t equal 6 and solve for t. So let's bring everything to the left. Let's get a common denominator. So here the 6 minus 9 is just negative 3. And then we get the common denominator, and this 9,000 over this. Now we can put the tops together, or the numerators together. All right, so we got negative 30,000 minus 9t and plus 90,000. Negative 30,000 plus 90,000 is just 60,000. All right, let's pull the leading coefficient of negative 9 out of the top here. There you go. And now there's only one way that this can equal 0, and that's if t is 60,000 divided by 9. So we can say after 6,666.667 approximately minutes, the concentration of pollutant in the pond will reach 6 kilometers per meter cubed. All right, part B, they want to know what will happen to the concentration of pollutant over time. All right, well, I probably should have factored this bottom earlier, but let's do it now. So really what we wanted was to see this leading coefficient. So it's negative 9 divided by 3. It matters here because this is a linear equation. This is of degree 1, and the bottom is also of degree 1. And since they're of the same degree, then the horizontal asymptote will be negative 9 over 3. That means as over time, in other words, the time is getting larger and larger and larger and larger, then that means that the value of the pollutant, so our C value, will be getting closer and closer and closer to negative 3, or negative 9 divided by 3, which is negative 3. All right, so that's represented by our horizontal asymptote. So it'll never actually equal negative 3, but it'll get closer and closer. All right, 3 employees work at a shipping warehouse. Tom can fill an order in S minutes. Paco can fill an order in S minus 2 minutes. Carl can fill an order in S plus 1 minutes. I'm already annoyed by how they do this because they don't do it, like if Tom can fill an order in S minutes, that doesn't tell me how many, we're not lining it up properly. S minus 2 minutes is a different amount of time than S minutes, so it's hard for me to monitor how much they're doing per minute. So you have to think of it this way. Let's say I can do an order in 5 minutes. So this is the amount of time it takes me, and I could do 1 order, the number of orders. Well, that means if you only give me 1 minute, well, I can only do 1/5. I only have 1/5 of the time, so I could do 1/5 of an order. If I have, let's say it takes me 10 minutes to do an order, so I'm even slower. 10 minutes to do 1 order. Well, that means if I only have 1 minute, well, I can only do 1/10 of an order. Let's say it only takes me half a minute, 0.5 minutes to do 1 order. Well, that means if I have 1 minute to work, so I have twice as much time, right? I have 1 full minute, I have twice as much time. That means I get 1 over 0.5 orders done, which is equal to 2 orders done. So no matter what, the number of minutes that it takes me to complete an order, it'll be 1 over that is the number of orders I can do in 1 minute. And that's the measurement I want. So let's start, instead of saying how long it takes them to do an order, let's say how many orders they can do in 1 minute. So let's change all that. So when I read this, I'm going to say Tom can fill an order in S minutes, but instead I'm going to write in 1 minute, Tom can fit 1 over S orders. And another way of looking at that is if he does 1 over S orders in a minute, then after s minutes, you have to multiply this by s, he'll do 1 order, and that's what it says. Can fill 1 order in s minutes. So that makes sense. Right, let's do this for Paco. He can fill an order in s minus 2 minutes, so I'm going to say he can do 1 over s minus 2 orders per minute. Okay, again, if I say this is the number of orders he can do a minute, and it takes him s minus 2 minutes, so you get s minus 2 minutes. Well, for s minus 2 minutes, you just multiply this by s minus 2 to see how many he can do, and that'll equal 1. And it says, yep, he can fill 1 order in s minus 2 minutes. So again, it makes sense. For Carl, he can fill an order in s plus 1 minutes, so that means he can do 1 over s plus 1 orders in 1 minute. When Tom and Paco work together, they can take about 1 minute and 20 seconds to fill an order. So let's just call that 1 and 1/3, so 1.3333 minutes to fill an order. A better way to write that is 4/3. And so how many orders can they do per minute if it takes them 4/3 of a minute to fill an order? How many orders can they do per minute? Well, it's going to be 1 over 4/3, which is 3/4. Whenever you do 1 over a fraction, it just gives you the reciprocal of the fraction. All right, let's continue. When Paco and Carl work together, they take about 1.5 minutes to fill an order. Or we can say 3 over 2. That way, orders per minute is 2 over 3. All right, so since we have the number of orders per minute, this t plus p is literally this many orders that Tom can do, and this is the number of orders that Paco can do. And so together, 1 over s plus 1 over s minus 2 will equal 3/4. Bring everything to the left, get a common denominator, combine all the numerators and keep the denominator. Now we can factor the top here, take out the -3 as the leading coefficient as well. So we see here s is either 2/3 or 4. All right, now when Paco and Carl work together, they could do 2/3 orders per minute. And that's combining the 1 over s minus 2 plus 1 over s plus 1. So these two added together will equal 2/3. So let's do all the same stuff to this equation. And now we actually run into a little problem here, because when you solve this, you get s is either a negative number or you get like 4.12 or something like that. And so what we're saying here is for this all to be true, s has to be like one certain number, like to solve this. But here, 4 and 2/3 both don't work here. Like if I plug in a 4, this is going to be 60, so 32 minus 1. So it's going to be -1, so +1 over 4. Well, it doesn't matter. Whatever it is, it's not going to equal 0 for sure. And a 2/3 also won't equal 0 for sure. So 2/3 squared is going to be 4/9, so 8/9 minus 16/3, so minus 32/9 and minus 9/9. It just doesn't work. So neither of these guys will equal 0. So we're saying that s has to be one of these two for sure, but also can't be one of those two. So this question is actually an impossible situation, unfortunately. Okay, number 14, compare and contrast different methods you can use to solve a rational equation. Make a list of the advantages and disadvantages of each method. I'll just talk about it. So one of the ways you can do it, you can solve, is by like algebraically the way I've been doing, by bringing everything to the left using subtraction and addition and then solving. The problem with that method is it takes a really long time sometimes, and it's just very tedious. There's another method. You could just multiply every term by the lowest common denominator, and that gets rid of all of your fractions. The problem with that one is that, so the advantage is that you get rid of your fractions right away, but a huge disadvantage is that when you get into inequalities, that method's not going to work for you anymore. It's going to run you into a lot of trouble. The third method is just a graph. Just graph both sides of the equations, or better yet, bring everything to the left, graph the left side of the equation, just say y equals the left side of the equation, and then just check to see where it hits the x-axis. And I'd say that's probably the best method of all of them if you have a graphing calculator handy. Yeah, I'm going to move on to number 15. I think that's enough to say about all that. If you have any direct questions about this, I could talk to you about it until the cows come home. Right, solve this equation, correct to 2 decimal places. Okay, let's start off algebraically and see where it takes us from there. All right, start off by bringing everything to the left. Then get a common denominator. All right, expand all this and bring it all together. All right, so I have a quartic equation up here, and this thing has to equal 0. So the bottom can't equal 0, and this must equal 0. So I was trying some numbers to see if I can reduce this down a little bit. I couldn't find any numbers. So actually I went and I graphed this on Desmos, and I'll show you what I got. So as we can see, all these zeros are at like kind of weird spots. Negative 3.8, negative 1.424, 0.897, and 4.328. So there's no way I would have guessed those guys. It would have driven me crazy. I never would have found anything. And so, yep, those are our solutions right here. The only way to make this equal 0 is if the top here, if x is equal to one of those 4 weird numbers. And that'll make the top equal 0, which means this whole thing will equal 0. I also did try just to see if I maybe made a mistake in this region. I actually tried plugging this original, well, the one where I just brought this guy over to the left, and here I'll show you what I got there. So you can see I kept that original green graph on here, and I also did, so that's this green graph is y equals this, and this purple graph is y equals this. So just to see if I did anything wrong in this region. But if you see, the solutions are still the exact same places. Right here is where the purple crosses and the green crosses. The purple and green both cross here, the purple and green both cross here, and the purple and green both cross here. So I didn't make any mistakes. I kept the same values of x that equals 0. It's just 4 really ugly values. So it's kind of mean for them to just say, oh, it says correct to 2 decimal places. So maybe that is a hint. All right, so the answer is negative 3.80, negative 1.42, 0.90, and 4.33. Those are our 4 answers, and we did need graphing technology in order to solve this one, unfortunately. Okay, number 16. Objects A and B move along a straight line. Their positions S with respect to an origin at t seconds are modeled by the following functions. Okay, when are they in the same position, and when is object A closer to the origin than object B? All right, I guess we should draw a straight line. All right, we'll make this the origin. And let's say positive direction is this way, and the negative direction is this way. So if s of t is positive 5, let's say, then that means it's like 5 to the right. And if it's negative 5, then we'll say it's like 5 to the left. Same with object B. Okay, so its position depends on the time. And so its position is just 7t over t squared plus 1. And the position of object B is just t plus 5 over t plus 2. And we want to know when the objects are at the same position. So when are they equal? All right, I think you guys have figured this all out. Bring it all to the left and solve. All right, now we're finding a common denominator. All right, expand, simplify, collect like terms, do all this stuff. All right, I got this far again, and I was having trouble finding numbers that would make the top equal to 0. And sure enough, once again, it's because they're ugly numbers. So I had to go to Desmos and graph this thing and see exactly where, like when I would let y equals this, see exactly where it does equal 0. And here you can see it crosses at 0.417 and at 1.705. Those are the only two answers. And you can tell the top is a polynomial of degree 4. And so we already see that this is going to have, it's going to go down, up, down, up. So it's not going to come down again because it's already done its 1, 2, 3, 4. Now keep in mind I only did the inside part. I only care about when that equals 0. If I had done the negative sign, it would have been all the same thing. It just would have gone, you know, like from this side, it would have been the mirror image like that, but it would have the same zeros. So when are the objects at the same position? So you can say that after 0.417 seconds and after 1.705 seconds, these objects will be at the same position as each other. Right? Now the next question is, here, let's move this. When is object A closer to the origin than object B? All right, this is actually a super interesting problem. And I think I just came up with a solution to it. So what happens is, the problem is, I can't just like subtract this to see if it's greater or less than, because this one could be greater than this one, but still be closer to the origin if they're in the negatives. Or maybe one will be in the negatives and the other will be a positives. And so it's really hard to tell which one's closer. But what if we were to square both of them? If we were to just take this and square it, and take this one and square it, then no matter what, they're both going to be positive all the time. And if this one was closer to the origin, then its square will be smaller than this one. And if it's farther from the origin, then its square will also be farther than this one. For instance, if one is at 4 and the other one's at -1, -1 is closer. But if you square them both, 1 and 16, 1 will still be closer than 16. So whichever one's closer to the origin, after squaring it, they'll both be positive, but whichever one's smaller after squaring it is the one that's closer to the origin. So what I'm going to do is I'm going to square this one, and I'm going to square this one, and then I'm going to subtract b from a. And if I get a negative number, then I know that a must be closer to the origin, because that means that b was a greater number. If I take a minus b and it ends up being negative, that means b was larger. And so that's what I'm going to do. I'm going to square both these things. I'm going to do a minus b, and I'm going to solve to see when it is above or below 0. When it's negative, we have a solution. When it's positive, we do not have a solution. All right, so as you can see, I set it up. So I squared both of them, and I subtracted object B, the distance from the origin of object B, from the distance of the origin from object A. Actually, the square of the distance from the square of the distance. So when this is negative, in other words, less than 0, that means that object A must be closer, because so this is smaller than this. And that's what we're looking for, right? When object A is closer to the origin. So I just have to go graph this. I'm going to do it on Desmos. And wherever it's below 0, that's where our solutions will be. So let's go check that out. All right, so from here in the screen, you can see that this one will be closer to the origin anytime t is less than negative 0.828 or between negative 5.16 and positive 0.417, and or greater than 1.705. Here, it's actually going to be farther from the origin, and here, it's going to be closer to the origin. Now, I don't like to the right and to the left. I'm like, well, I don't know if it goes back up again somewhere way off. But if you kind of look at this, you can see as t starts to get big, this right here, 5 over t plus 2, will start getting smaller and smaller and smaller and smaller. And so this will actually just kind of level off just at t squared. Whereas this guy, t is going to get really, really large on the bottom compared to on the top. So this is going to get very, very small. This is going to go up and blow up real fast. And this is just going to keep getting smaller and smaller and smaller. And so this one's going to be much larger as t gets larger. And that won't change for negative numbers because, I mean, the same thing. This is going to just go off to close to 0 real fast, and this will go off close to 0, but this will just be a negative t basically left when you get really big. But when you square that, it's still going to be a positive number, so it'll still be very, very large compared to this one. So this one will often be closer to the origin. So the only time it's not closer to the origin is between negative 0.828 and negative 0.516, and also between 0.417 and 1.705. And then after that, it'll always be, this guy will always be closer to the origin. But also, you know, there's always a question, do you count negative time? I often do count negative time, right? It's just time in the past. And it doesn't really say anything about their position in respect to at t seconds. It doesn't really say like that you can't have negative time. So t might just be seconds starting on January 1st, but it's been going for years. So that's another thing to consider. All right, I think we are done this homework.